All right. Good afternoon, everyone. We'll get started. Okay, so I'm going to quickly talk about our final project. So the project is essentially an opportunity for you guys to apply what you've learned in class, and I really want to try and make it useful for you guys. So to the extent that you're maybe doing some data analysis already, maybe for research or something like that, that's perfectly fine as a topic to use for the project. I should mention that you guys are welcome to work in groups. You can have up to 3 people in a group, but you can work solo as well if you'd like. It's up to your own preferences. And then we do have some deliverables. So in a couple of weeks, you need to submit your project proposal. So that is due on May 8th. Project presentations are going to be the last week of class, June 2nd. And so the project presentations are going to be due at the start of class because we're going to split up the presentations Tuesday, Thursday. So the folks on Tuesday who are presenting on Tuesday have kind of the same amount of time as you guys. It'll be fair so that all the presentations are due at the start of class at the beginning of the week. I will mention that I am attending a conference that week, so I need to figure out what we're going to do for that. So I think preliminarily I would like folks to still come and present so that you guys can share your work with the rest of your peers and get feedback that way. And then we'll have to have some kind of recording or something so that I can view your presentations as well. Maybe I'll talk to you about ways we can do that. So just as a heads up, sorry for the inconvenience. But you will get feedback from me on your presentations that you can then incorporate for the final project, which are due like the Thursday or Friday, whatever the limit is that Canvas allows me to do on the finals week. Okay? Any questions about the projects? So you can find more guidance on Canvas. The rubric is already available. I can talk a little bit about the general sort of project or the pieces of the final project. So in the proposal, you should have identified a data set that you'd like to be using. And I'll mention that the stuff that you're putting in your project proposal doesn't commit you to working on that particular data set or that particular problem. But this is to make sure that you guys are starting to look at this ahead of time. You don't want to be scrounging around for data sets last minute. I want folks to have spent some time to already think about this and try and grab data and think about what they'd like to do for the project by the time you're doing this proposal. And if things change over time, that's totally fine, but we at least want you to get started by this date. Project presentations, up to 15 minutes. Again, I'm not gonna go through this in too much detail. I'll just say take a look at the course project guidelines. This gives a more thorough ask of each of the components as well as a rubric, so you guys know what we're looking for in this class. And that is online on Canvas already. Okay? Questions? Alrighty then. Everyone will know everything you guys have to do for your project then. And yeah, feel free to reach out to me if needed. If you want to talk about your project proposal before you submit, I would recommend that you do so. And I'm happy to help with figuring out ideas and helping with getting data sets as well. All right? Okay. Let me close a couple of these guys. Okay, so we will go ahead and jump into our lecture today. So we are currently on, why is my pen not working? Ah, great, out of batteries. Okay, that's fine. I will use my finger. Sorry for the atrocious handwriting that's about to happen. All right, we're on lecture 7. Okay. All right, so today we're going to be talking about model, oh my God, selection. Yeah.
Do you want to try this?
Yeah, actually, if that, I'm not sure it'll work. This is like Apple Pencil stuff, but maybe. Oh, okay. Oh, wait, it does work. All right. You come very prepared for all of my inadequacies. All right. The tip is still kind of big, but we'll make do. Oh, this is maybe not. Okay. Okay. So model selection. Anyways, we'll get through this. I'll probably be able to use the Apple Pencil in just a couple minutes. The task of selecting a statistical model from a set of candidate models. Okay, so let's see. I'm going to try this. Okay, so suppose we have data that looks something like this. Y, x1, x2, x3, and so on, right, all the way to xn. So this might be like your typical data set, right? You've got a big data table with a bunch of columns of different variables, and we want to figure out, right, you have y is equal to beta 1 x1 versus y is equal to beta 2 x2 versus ... and also this way, in this dimension as well, right? We could go all the way down to y is equal to beta 1 x1 plus beta 2 x2 plus ... beta n xn. So there are a tremendous number of combinations that you could probably come up with of different variables, depending on your kind of starting set. And so our kind of fundamental question is, of all of these things, which model is best? Right? And I guess let me ask a pointed question here. So if we look at like these univariate models compared to a model that includes all of our variables, which one would you guys say is more simple versus more complex?
The univariate ones.
The univariate are more simple. Yeah, that's right. So thinking back to last time about this model complexity and having, a total error that minimizes the sum of our bias and variance terms. We're trying to do this balance between having a simple model versus a complex model. And so to some degree, you guys can think about like these ones maybe are not complex enough to get over our bias error. And at the other end of the spectrum, these models might be overfitting, right, and leading to too much error in our variance terms. And so we need to think about strategies to determine, where's the sort of proper place, where's the proper level of complexity to get to, right? And so this is very much following in the same train of thought with a specific application to thinking about complexity of models as it relates to the variables in our model. Okay, let me see where I'm at now. Oh, okay, sweet. That didn't take long. Okay, so let's just do a new page. So let's talk about some criteria for model selection, and I'm going to cover some of the most common ones used in the field. So criteria for model selection. Okay, so one is I never know how to pronounce this. I think it's Akaike information criterion, but I could be totally wrong. This is commonly known as AIC. This is an estimator of the relative quality of a statistical model. And smaller is better. So AIC for reference looks something like this. 2k minus 2 times ln of our maximum likelihood. So k represents the number of parameters. And L is our maximum likelihood value. So when you look at the structure of this equation, there is kind of an important concept to think about, which is the idea that going back to this bias versus variance thing, right? So we have bias that looks like this, variance that looks like this. and then total error. I'm just going to say TE that looks like that. A lot of the criteria that we're going to see and the concept of what we're trying to do is about balancing the reduction in bias with the increase in variance. And the way that this is represented, right, so we have model complexity on the x-axis. So your maximum likelihood value is essentially saying is a different way of kind of reducing your bias, right? So the larger your maximum likelihood value is, you're kind of saying in some ways the better the fit is. And so what's happening in the AIC? 2 times natural log of the maximum likelihood value. So as your MLE or maximum likelihood goes up, what's happening to your AIC? It's, sorry, what was that? It's going down, right? Because you're subtracting by a number that's getting bigger. Okay. So that's kind of like doing this. You're decreasing in your bias. What about number of parameters, right? So we just talked about this, right? Univariate versus multivariate models. Which one is more complex? The multivariate, right? So the more variables that we add, then the more complex we're getting in this side of things. And so you are increasing your variance term. And this is essentially a proxy for that, right? Because as we add more parameters, what's happening to our AIC? It's getting bigger. And we prefer a small AIC, right? So as you add more parameters, you will be increasing your maximum likelihood value, but then the 2K term will start increasing. And at a certain point, it's like, oh, no matter how many variables I'm throwing in here, my maximum likelihood value isn't getting much better, but my 2K thing continues to penalize my AIC. So this is, again, the fundamental balance between bias and variance that's trying to proxy for getting at, right, our lowest total error in some ways. Okay. And I'll just note, so there's a special case of this for linear models. AIC will actually reduce to 1/n sigma squared times residual sum squared plus 2 d sigma squared. Yeah, I wouldn't worry about this. This is reduces to this for linear models. This is more if you ever encounter this equation somewhere, you just know that this is the application of AIC for linear models. This is commonly how it's written. Okay? Okay, any questions about AIC? So we can think about AIC as a metric with which to judge specific models. And if you're comparing different models, you can look at the AIC and see, oh, which one actually has a smaller AIC value. That means it's probably doing it, like the estimator is probably a better model than the other in terms of trying to reduce that total error. Okay. What other metrics are there? So we've got something called Mallows CP. This is going to look kind of similar. This reduces the residual sum of squares while taking into account the number of parameters. And this actually ends up being equivalent to AIC for linear regressions. At least proportionally. Okay. So this looks something like this. CP equals 1 over n times RSS plus 2 times K sigma squared. So this is our sample size. Residual sum of squares. And then our number of parameters. And then this is our estimate of variance. Okay, so looking at this equation, very similar type of thing, right? So as our model gets more and more complex, as we throw more variables at it, our residual sum of squares will decrease, right? And so you're decreasing your bias term, but then we penalize having too many parameters. So we're adding more variables, you're decreasing your residual sum of squares, and your 2 times k times sigma squared value will start to go up. And so this is again doing this balance between reducing the bias term and then increasing in the variance term. Yeah?
I have a question to the ALC.
Okay.
Because can you only compare models of the same order? Because if you are taking 2k into account as a formula, this grows by decreasing model complexity. But
Yep.
then 2ln can never go larger than 2. So I would expect the ALC for more complex models to be higher. And if we're saying the low ALC is a good or is better, then the value would be larger for more complex models. Wouldn't it be?
The limit for 2 times ln L is not 2, is it?
Oh no, it's not 2, but like you know how ln kind of
Yeah.
shadows. So I would expect to generally get a lower ALC.
This was devised, this equation was devised in such a way that the area in which you're like plateauing, you're usually operating in that margin. And so there is this kind of trade-off. You do see a very distinct trade-off where at least in kind of the reasonable size, like going from 1 variable up to maybe like 1,000 variables, you're likely still observing a decent trade-off between your 2k and the latter term.
Okay, so it can still be used for
Yes.
comparing models of different orders.
Yes, absolutely. In fact, it's mainly used for that. Yeah. The amount of variation you see when you have k as a fixed, so fixing the number of parameters and just affecting the likelihood, oftentimes that's smaller in magnitude than the changes when you're like freely adding and subtracting variables into your model. But yeah, good insight. So these are not perfect. Certainly, there's some limit to where you're going to taper off in your ability to contribute, like on the latter part of it. And we'll talk about that as a drawback in comparison to some of the other metrics. Yeah.
Thank you.
Any other questions? Yeah.
Is now CP widely used in actual researches because the mallow CP is like a special case of AIC when it is a linear regression model, and like why would we use this like specific, I mean like
Ah.
a separate CP instead of just using AIC?
Yeah, so MalloCP, it's not that it's a special case just for linear regressions where it is more that is a different way of doing this metric that looks like an AIC when you're doing it for linear regressions. But you can apply a MalloCP to nonlinear regressions as well. And the idea is more that I'm calibrating to the RSS as opposed to the maximum likelihood. So in some cases, people prefer to look at RSS. I'm actually not sure the like true application difference between mallows and AIC.